All right, welcome to your last video of the week. This is section 6.4, part 1. We're going to do part 2 next week. Today we're going to talk about polynomial division and rational roots. The objectives in this lesson, we're going to divide polynomials with something called synthetic division, determine possible rational roots of a polynomial, and then we'll be using that in our lesson next week, and then determine if a linear term is a factor or if a constant is a solution to a polynomial. So first we're going to review what we call the division algorithm, just some division terminology that you probably learned way back in the day, like elementary school when you first learned how to divide things. So we're going to be applying this to polynomials, but these terms will continue based on what you learned about division in the past. The first term is a dividend. The dividend is what your original number is that you're going to be dividing something into. So for us, we're going to use an f of x to represent that, and we're just going to call it our original polynomial. The next term is a divisor. The divisor is what you are dividing into, the original polynomial, and we're going to use d of x to represent that. So the dividend and the divisor make up our problem. The quotient is how many times the divisor goes into the dividend. So how many times evenly your number goes into what you started with, or your polynomial goes into the polynomial that you started with. And then we're going to use r of x to represent the remainder. The remainder is what's left over, and that's always going to be smaller than your divisor. The algorithm that we can write to relate all four chunks to each other are dividend, our original problem, equals the divisor, what you're dividing in, times the quotient, how many times it fits in, plus the remainder, what's left over. So it's another way to write our original problem after we've divided. If our remainder is the zero polynomial, or r of x is less than the degree of d of x, meaning your remainder is smaller than your divisor, you know you've done this problem correctly. And being the zero polynomial will be a special case that we'll talk about in a little bit. But you always want to make sure that your remainder is either zero or smaller than your divisor. And because we're talking about polynomials, it'll be a smaller degree than what you started with. So you know you've completed the problem. Now, there is long division of polynomials, which we do not cover. What we're going to talk about is synthetic division of polynomials. Synthetic division is when you have a linear divisor, meaning what you're dividing in, the highest power is a 1. If it's a higher power than that, you would have to use long division, which again is not something that we're going to discuss. Now, I put these steps on here for you to refer back to if you need to. By no means do you need to write all these out, or do I think you should write all of these out. After we do a couple of problems with synthetic division, you'll get the procedure. But if you feel like you need something to refer back to, I did put the step-by-step process on here for you. So synthetic division is dividing a linear term, something like this, x minus 3, into a polynomial, something that has a higher power. So we call what we're dividing in the divisor. This is that d of x. And what we're dividing it into is the dividend, what we're starting with. To start synthetic division, we're going to write down the coefficients of our dividend, what we're starting with, f of x. Coefficients mean numbers in front of the variables. If you are missing a variable power, so x squared, x to the first has a negative, or x to the second has a negative 7 in front, you'll notice I don't have an x to the first at all in this problem, so we're going to put a 0 as a placeholder for that, and then a 5. So I've got all my powers accounted for, 3, 2, 1, and then x to the 0, or my constant. To find the number that you're going to use in synthetic division that's going to go in this wonderful little box, we take our divisor and we set it equal to 0. So eventually this is going to represent a possible factor of our polynomial. And when we set it equal to 0, we're finding a solution or an x-intercept that we'll be testing. So x equals 3 is going to go in my box. Okay, to complete synthetic division, we're going to bring down our first number always, and it stays the same. Then we're going to multiply what's on the bottom times the number in the box. So 3 times 2 gives me 6, and we're going to fill out one column at a time. To complete the column, we're going to add down the column. So negative 7 plus 6 gives me negative 1. And then we repeat the process. 3 times a negative 1, negative 3. 0 and negative 3 add to negative 3. 3 and negative 3 give me negative 9. Add down my column, negative 4. The last number that you're left with will always be your remainder. So we would say r of x here is equal to -4. The other numbers that you're left with represent your quotient, how many times the divisor went evenly into your dividend, into your original polynomial. Now, when we start with a polynomial, we want to note its degree. Our original polynomial was a degree 3. Every time you do synthetic division, it's going to take your polynomial down by 1 degree. So the quotient will always be 1 less degree than what you started with. That tells you what variables to put back in and what powers. So that 2, if it's 1 degree less than what we started with, will be an x squared. The -1 will be an x. And the -3 will be our constant. So this now makes up the solution to our division problem. The quotient is how many times the divisor goes in evenly, and the remainder is what's left over. If you want to check this answer, you can check it with the division algorithm. The division algorithm says the original problem equals the quotient times your divisor plus your remainder. Now to check here, you would have to simplify. You'd have to do a larger foiling problem here. Distribute, multiply everything in the first parentheses by everything second parentheses, combine your like terms, add -4, but you should, if you simplify that right side, be equal to your original polynomial on the left. So that's the division algorithm if you want to check that those two expressions are equivalent. Let's try another one. Here we're dividing in x plus 4. So I'm going to set that equal to 0. Solve for x. X equals -4. That's what's going to go in the box for my synthetic division. Coefficients of my variables are going to go in my top row. So 2, x to the third, 1, x squared, -18x, and -7. And I'm not missing any variable powers there, so I don't need any zeros in this example. Bring down my first number, and then we're going to multiply and add. Multiply, -8, add, -7. Multiply, 28, add 10, multiply, -40, add, -47. So my quotient, q of x, is again going to start with a power of 2 because my original polynomial was a power of 3, minus 7x plus 10, just those variables going in descending order. And my remainder is what's left over. It will always be a constant, 1 degree less than what we were dividing in, -47 in this case. Okay, here's one for you to try. Be very careful with the zeros here. You're going to need a lot of zeros to account for the powers that are missing. Okay, so 1x to the 5th, 0x to the 4th, 0x to the 3rd, 0x squared, 0x, and a 1. And if I set x plus 1 equal to 0, I get x equals -1. That's going to go in the box. Bring my first number down. Multiply and add. Multiply, -1, add, -1. Multiply, 1, add, 1. Multiply, -1, add, -1. Multiply 1, add 1. Multiply -1, add 0. So I started out with a degree of 5, which means when I write my quotient, this will begin with a degree of 4. So 1x to the 4th, and if you want to put the 1s in there, that's fine, minus 1x to the 3rd, plus 1x squared, minus 1x plus 1, and my remainder here is equal to 0, which tells me that x plus 1 divides in evenly. Okay, our next theorem to go along with our division is about solutions and factors. A polynomial is a factor of a polynomial if and only if that the quotient times the divisor equals the original polynomial, aka there is no remainder. So if we look back at this problem that you guys did a second ago, we can say that x plus 1 is a factor of x to the 5th plus 1 is what that remainder of 0 tells me. And that means that I've actually, by doing this synthetic division, factored the original polynomial. If I write it out with that division algorithm, x to the 5th plus 1, it's equal to the divisor times the quotient. And then I can put plus 0 at the end if I want for remainder, but adding 0 isn't going to change anything. So you can see we have a factored version of the original polynomial anytime we have a remainder of 0 because we don't have that extra piece added on at the end. So this is going to be really helpful for problems that we're unable to factor by hand, so we don't have to use technology to solve them. So let's look at this next problem. We want to determine if x minus 2 is a factor of this polynomial. So to do that, we're just going to use synthetic division, divide it in, and look for that remainder. So I'm going to start x minus 2 equal to 0. X equals 2 is what's going to go in the box for my synthetic division. 3, 2, negative 19, and 6. Bring down my 3. Multiply, add, multiply, add, multiply, add. Now the problem here is not asking what's the quotient, what's the remainder. The question says determine if it's a factor, and the answer here is yes, it's a factor. And if you had to explain why, you could say because the remainder is equal to 0, because it divides in evenly. X minus 2 is a factor. A similar theorem is that a, some number, is a solution to a polynomial if and only if the remainder when we divide in by a is equal to 0. So very similar here. Actually, in the last problem, 2 would be considered our a value. When we're talking about an a, we're talking about that number that we get as a solution when we set the factor equal to 0. So in problems like this, determine if negative 3 is a solution, and remember another word for solution is 0 or x-intercept or root. If you see any of those, it all means the same thing, and it all means that we're going to consider that our a value, we're going to put it in our box, and we're going to use synthetic division. If, again, we get that remainder of 0, it's telling me I have a solution. And then going along with that, it tells me I have a factor, and I can factor the polynomial, which will be nice for later. So my coefficients in this problem are 1, 3, negative 5, 8, and 75. Again, I am not missing any terms here, any powers, so I don't need any zeros as placeholders in my synthetic division. I'm going to bring down my first term, 1. Multiply, add, multiply, add, multiply, add, multiply, add. So to answer the question, determine if negative 3 is a solution, our answer is no. Negative 3 is not a solution. Again, because the remainder is not equal to 0. It's equal to 6 instead when I divide negative 3 into the polynomial. Okay, here are a couple for you to try using the factor theorem and the 0 theorem. In number 1, you want to determine if x plus 2 is a factor using synthetic division, and in number 2, you want to determine if negative 1 is a root using synthetic division. Okay, so you should have put negative 2 in the box for the first synthetic division. 3, negative 1, negative 20, and negative 12 are my coefficients. Bring down 3, multiply, add, multiply, add, multiply, add. So, yes, x plus 2 is a factor because the remainder is equal to 0. To determine if negative 1 is a root, remember root means solution or x-intercept or 0, all the same thing. Negative 1 goes straight into the box. 5, 8, 1, 2, 4. Again, no missing coefficients there, so I don't need any zeros. bring it down, multiply, add, multiply, add, multiply, add, multiply, add. So again, you get a yes here. -1 is a root or a solution, or if you looked at the graph, an x-intercept, because my remainder is equal to 0. Okay, the last theorem that is in this lesson, which is kind of a lead-in to the lesson that we're going to do next week, is the rational roots theorem. So ultimately what we're building up to here is to be able to solve a polynomial that cannot be solved using factoring methods, to find all its zeros or roots or x-intercepts. And to start that process, we use what we call the rational roots theorem. The rational roots theorem creates a list of possible, that's a key word here, roots or solutions to the problem. Now it's only rational roots, meaning only solutions that can be written as a fraction. So fractions and our integers would appear on this list. It will not give us the list of possible irrational numbers like square root of 2 and square root of 3, but at least it'll be a starting place for us. If there is a solution to an equation that's rational, it will appear on this list. To create the list of possible rational roots, we're going to create two sets of numbers, p's and q's. P's are going to be factors of the constant term, and Q's are going to be factors of your leading coefficient. All the possible P's over Q's are going to be possible rational zeros of the polynomial. So we're going to do a couple of these together so you can see what this looks like. And again, we're not solving the polynomial here, we're just creating a list of numbers that could be possibilities. So if I'm looking at my first polynomial, I'm going to make lists of p's and q's first before I put them together to make a list of p over q's. P's come from your constant, the number without a variable. Q's come from your leading coefficient. So we're in it for right now, ignore the positives and negatives. We're only going to think about just the absolute value of these numbers. So I'm looking at p is 3. Factors of 3 are 1 and 3. Q is 2 here. Factors of 2 are 1 and 2. So now we want to put the numbers together. Possible values of p's over q's are all the ways that a p can be divided by a q. So you want to try to do this in an organized manner if you can, because these lists can get long. I usually start with the first p and divide it by each q, and then go to the next p and divide it by each of the q's. So 1 divided by 1 would give me 1. 1 divided by 2 would give me 1/2. And notice I'm putting pluses and minuses in front of each of these because now is where we're going to count for all the possible positive and negative values within this equation. Then I move to the next p. 3 over 1 is 3 over 1, so just 3. And 3 over 2, 3 over 2. So there are technically 8 possible rational zeros to this polynomial: positive and -1, positive and -1/2, positive and -3, and positive and -3/2. And then this is the list we'll use as kind of a jumping point when we actually solve polynomials in part 2 of this lesson. Okay, let's try another one of these. In this problem, p is 8. So we want all the factors of 8, numbers that multiply to 8. 1, 2, 4, and 8. My possible values for q are all the numbers that multiply to 6. 1, 2, 3, and 6. Now putting those lists together, I create my list of possible rational zeros, p's over q's. And don't forget plus and minus in front of each number to account for our positive and negative values. So starting with the p value of 1, 1 divided by each of these q's will give me 1, 1/2, 1/3, and 1/6. Now I move to my next p, 2. 2 divided by each of my q's. 2 over 1, 2. 2 over 2 is 1. It's already on my list. I'm not going to write it again. 2 over 3. I don't have that one yet. And 2 over 6 is 1/3. It's already on my list. I don't need to write it again. Next, I'm going to use p-value of 4. 4 divided by each of my q's is 4. 4 over 2 is 2. It's already on my list. 4/3 is not on my list. 4 over 6 is 2/3. It's already on my list. Finally, 8 divided by each of my Q's. 8. 8 over 2 is 4. It's already on my list. 8 over 3. And 8 over 6 is 4/3. It's already on my list. So I actually don't need that last comma there. We'll get rid of that. And so now the number of possible rational zeros are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20 possible rational zeros on this list. Okay, try this one on your own. I want everybody to make a list of p's, numbers that multiply to, well, I'm not even going to give that away. A list of p's, a list of q's, and then your list of possible rational roots, p's over q's. Okay, p's here are numbers that multiply to 48, so we've got a lot of them. 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. Q's are numbers that multiply to 6. 1, 2, 3, and 6. Possible p's over q's. 1 divided by each of them. 1, 1/2, 1/3, 1/6. 2 divided by each of them. 2, 2/2 is 1, 2/3, and 2/6 is 1/3. It's already on there. 3, 3/2, 3/3 is 1, 3/6 is 1/2. They're already there. 4, 4/2 is 2, already there. 4/3, 4/6 is 2/3. It's already on there. Then 6, 6 divided by 1. 6 divided by 2 is 3. It's already there. 6 divided by 3 is 2. It's already there. 6 divided by 6 is 1. It's already there. 8, 8/2 is 4. We've got it. 8/3 we don't have yet. 8/6 is 4/3. We've got it. 12, 12/2 is 6. 12/3 is 4. 12/6 is 2. All of those are on the list. 16, 16/2 is 8. 16/3, I don't have that one yet. 16 over 6 is 8/3. It's already on my list. 24, 24 over 2 is 12. 24 over 3 is 8. 24 over 6 is 4. They're already on my list. 48, 48 over 2, I've got 24. 48 over 3, I've got 16. 48 over 6, I have 8. So here is my list of possible rational zeros, and let's count them up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, including all the pluses or minuses. There are 36 possible rational zeros. So we'll be using synthetic division and rational zeros in part 2 of this lesson.